We're looking at some statistics today. Rather than doing sequence and series stuff, it kind of ties in to the end of this chapter, and we're going to look at ways to display statistics. And we're going to look at what our calculator can do to help us do that. To begin with, I handed out in class some statistics on Peyton Manning and Eli Manning, and we're going to do some comparison. We put in their passing yardage, because they're both quarterbacks, their passing yardage. We put Peyton Manning's data in list 1, and then we put Eli Manning's in list 2. If you have that packet, then go ahead and take maybe a minute and go ahead and enter that data. If you don't, then you're just going to have to follow along, and that'll work as well. If you want to enter your data, pause the video, go do it. Otherwise, I'm moving on. All right, so the first thing I want to show you is an area in your calculator where you can find one variable statistics. If you have your data entered in your list, then you're going to go to Stat, Calc, and the very top option is one variable statistics. Now, it defaults to using list 1, but if you want to use a different list, you have to indicate that before you press enter to actually calculate the statistics. So make sure you pick out what list you want. Different calculators do this differently. You should be familiar with yours. When I press enter and I calculate those statistics, this right here is the window that comes up. Let's talk about what this shows you. There's some new notation here that you probably don't know. So this term right here, this is called X bar, and X bar is the mean of the data. It's the average. I bet you could guess what this finds for you. What's that sigma notation mean? Okay, that is the sum of all of my data in that particular list. This is the sum of all that data squared, and there's different things here that you would use in a stats class. We're going to pick out the key stuff that we want. So X bar is definitely going to be something we will use. This one right here we will also use. This is a lowercase sigma. Looks like this. It's a circle with a little line across. And this is the standard deviation. This indicates how far values tend to vary or deviate from the mean. So if you have a large standard deviation, then your data is pretty spread out. If you have a small standard deviation, then it's close together. We will need that value. N is going to tell you how many data points there are. And then you think you're done, but you don't. You're not, because you can scroll down. If you keep scrolling down, 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 you get this information here. Here you can see there's that N again with 10 pieces of data. And then the next thing that they give us here is what we call the 5-number summary. It's the minimum value, it's the maximum value, it's the median, and then it's the 2 quartiles. This 5-number summary here kind of breaks your data up into fourths, where if you had 40 pieces of data, you'd have 10 pieces of data that fall between these values, you'd have 10 pieces that fall between these values, 10 pieces that fall between here, and 10 here. That's what that 5-number summary is. So let's go ahead and jot that down. The 5, well, I don't need to redraw it because it's in the, it's on the screen there, but this right here is what we call the 5-number summary. And we're going to use the 5-number summary to make a box plot. Now, I think I called this Peyton Manning's data. This is actually Eli Manning's passing yardage. So you can see that it represents 10 different seasons worth of how far did he pass for the whole season. And so that's what these numbers represent. And I'm going to make a box plot using this 5-number summary. The first thing you're going to want to do is create a number line that would match the data. In this case, I'm going to look at my minimum and say, I think 1,000 would be a nice number to put in as a minimum. And then I'm going to look at what the maximum, I think a maximum of 5,000 would probably be appropriate. So I'm going to probably do, like, this is going to be 1,500, and then here's 2,000. There's 2,500, there's 3,000. 3,500, 4,000. And then 4,500 and 5,000. And then I'm going to plot the 5-number summary. So I have a minimum of 1,043. Obviously, with this large of a scale, these aren't going to be super accurate. We just want ballpark. And then I've got a 3,200-ish for my quartile, and a 3,500 for my median, 4,000-ish for my quartile 3, and my max was pretty close to 5,000. Now with these 5 numbers, we create what we call a box and whisker plot. And with the quartiles, I create my box. And then from the quartile out to the min and the max are what I call my whiskers, and I draw a bar right down through that last dot, that median. That bar always shows the where the median is of the data. And there's your box and whisker. Okay. Now, I wanted to talk about some other statistics that this 5-number summary can give us. One of those things is the range. You're probably familiar with that term. The range is basically how spread out the data is. You're going to find that by taking the max and subtracting the minimum. So you've got the 2 numbers you need, you would just subtract those values. Then we have the interquartile range. The interquartile range tells you the range from quartile 1 to quartile 3. If you look at your box and whisker, it's basically telling you how big the box is. That's what the interquartile range is. So I'm going to subtract those 2. I'm going to find that by taking Q3 and subtracting Q1. And then the other thing that I want to talk about is outliers. Now we can say something is an outlier if it stands out from the rest of the data, but there's kind of got to be a cutoff. Just because it stands out, does it stand out enough to really be considered an outlier? When I look at this data here, this seems like a very low point compared to the rest, but were there other low points down there also, or was it like a bunch of them up here and then there was this one way down here? It's hard to see on that box and whisker, but that's what we want to do, is we want to identify if there are any outliers. So to do that, we have a little formula that we use to designate whether it's officially an outlier. We take the interquartile range and we multiply it by 1.5. I don't know what's magic about that. That's just what we do. Interquartile range times 1.5. Now, I've gone ahead and done the math on that. And so my interquartile range I went and found to be 764. And if I multiply that times 1.5, I get 1,146. Now, this is the number that we're going to look at to determine if we're going to have an outlier, because we base it off of basically how long these whiskers are. This right here is quartile 1. I'm going to take quartile 1 and I'm going to subtract this 1,146. And if I have anything down here that far, I'm going to consider it an outlier. And then I'm going to turn around and do the same thing from quartile 3. That's the top end of the box. And I'm going to add the 1,146 and see if there's anything up there high enough that I would consider, if it's beyond that distance from the quartile, then it's going to be an outlier. So if I take quartile 1 and subtract that number, or if I take quartile 3 and add that number, and if I have any numbers out there, it's going to be an outlier. All right, so then in my calculator real quick, I got 3238 is quartile 1, and if I subtract 1146, I get 2,092. Okay, now if you look, now I know you don't have all of the data in front of you, but you can see that the minimum is a 1,043. That is substantially lower than 2,092. So that 1,043 is an outlier, because it's that much lower than the actual quartile. That's kind of an important deal, because what that means is I am not going to actually draw my whisker clear out there to that outlier, because that was out of the norm, and I don't want my box to represent it as though that was normal. So what we do instead is we will modify this box plot. Real quick before I do that though, I'm going to take my quartile 3, 4002, and I'm going to add the 1146. And there I get 5,148. If you look back at your maximum, that wasn't in the 5,000, so that's not high enough to be considered an outlier. You might have more than one outlier. If I had my whole list of numbers, and I might have multiple lower, maybe I have this one and another one's down here. I think as I recall, this was the only point, and then the other ones were up here. Typically what we do then is we will modify our box plot. So to modify the box plot means to write the outlier as like a little asterisk or a star instead of drawing the whisker clear down to the end. So here's what it would look like if I tried to modify it. I'll draw another one kind of above it so you can see it. All of this would be the same. I'd still have that, I'd still have this, but down here instead of drawing a whisker, I'd put a little asterisk out here. And then my whisker just gets drawn to the next lowest number, which I don't have my list of numbers, I don't know right off, but I would draw this down to whatever the next lowest was that was not an outlier. All right, so we like to modify it. This is the modified version, and this is what we will use. Now let's go to your calculator. We're going to let the calculator make that box plot. I think it's helpful to see how it's built so you know what's going on, but I do want you to know the calculator can do it for you. The first thing that you do, just like when we made our number line, you need to create a scale that's going to work. So you go into your window and you create a scale for your x-axis. It's only one variable, so you're really only using your x-axis on this. I usually just go 0 to 5 for my y values. And then you can see this was kind of what the scale was I used. And then you're going to go to, and I don't have a screenshot of this, so it might help if you had your calculator, but you're going to go to stat. No, you're not, sorry. You're going to go to second y equals. And remember, that's where you pick out that you do a scatter plot. So second y equals is your stat plot. And you press enter on number 1, and you'd go turn it on. And then you can, on the type, you can see the very first thing that we tend to always use is that scatter plot. But you have other options. If you go right, you get down here to see, and you can see some little box plots. There are 2 box plots. You want the first one because it's modified. You should be looking at your calculator here. The first one, you can see the little outliers are separate. So you always want the modified box plot, and you'd pick that. And then you pick what list you're using, and the mark is usually going to be the little box or the plus sign because that's what the outlier would graph like. So, and then you just press graph. After you have the right window, you just tell it, hey, I want a modified box plot, and it's going to do it for you. Okay, and then this is what it should look like, just like ours did, where it shows the box is up here. The whisker, notice, does not go all the way to the outlier. It keeps the outlier separate as a little box. So this is Eli Manning's passing yardage. Now, the point of a box plot, why do we use it? Well, what it does is it shows the spread of the data. That's what's important for you to know, that the box plot shows you how spread out the data is. When I look at this, remember I had already mentioned that it splits your data into fourths. So 1/4 of your data is here. So again, I had said if there were 40 pieces of data, 10 of them fall here, 10 of them fall in there, 10 fall here, and 10 fall here. So what's it mean to have 10 of them in this little space and still have 10 of them in this big old wide space? Well, it doesn't mean, and it's very tempting to think there's so many more points down here than there are in here. But there's not. There's 10 in each of them. The fact that this is a skinny little section means that they are very condensed. They're very close together, whereas these were very spread out. That's what I mean by it tells about the spread of the data. What I would say then when I'm looking at this, well, tell you what, let's do this. I also have a scatter plot, I'm sorry, not a scatter plot. I have another box plot of Eli Manning's data, passing yards. And then I just went in and I went into stat plot and did a second plot. My second plot, I made another modified box plot. And I used the other list so then I can compare. It's important when you stack these box plots that you label which one's which, because otherwise I'm not going to know. This top one was Eli, and this one is Peyton. And it's really neat to see the two box plots together, because if I were comparing these two quarterbacks, who do you think is the better quarterback? Well, there's a couple things that you should notice about this. Obviously, Peyton's data, his passing yards in general, are much higher than what Eli's are. In fact, almost all of his, right here, except for this one outlier year, almost all of his were better than half. See how this is the middle? This is the median? That's halfway on Eli's seasons. So Peyton is better than Eli half the time. Well, and that's not even, it's more than that. It's just that all the time he's better than Eli was half the time. You can just tell the numbers are so much higher. Now, the other thing I want you to really notice, and this is what I like to talk about, is the how compact Peyton's box is. If it's very compact, that means he's very consistent. That's the word I like to use. He's consistent. He typically has values. His passing yards typically stay rather close together. That keeps him consistent. We kind of know Peyton's going to fall pretty much in this area right here, whereas Eli's got quite a range of values that he's going to fall. The more compact it is, the more consistent they are. All right, I think that's all I got on box plots. Let's move on. Now let's take a minute to look at a different type of statistic other than a box plot or that 5-number summary that does a great job of showing the spread of the data. Let's look at something different. Let's look at a weighted average. Typically when we find the average, we always think of the mean. And the mean is when you add up all the numbers and you divide by how many there were. But sometimes, and this happens a lot with grades, you have what we call a weighted average. Not everything gets the same weighting in the grade. So if you look at this example, for JC's math grade, her tests actually weigh 80% of her grade. And then her quizzes are only 10% and homework is only 10%. So a lot of weighting goes into the tests. So how does a teacher figure out how to determine that grade? Here's how this weighted average would work. You take what JC's homework average was. Okay, that was a 96. And you're going to take 96 and you're going to multiply it by what weighting it gets. And this was a homework average, and up there it said that homework is 10%. So I'm going to take it times 0.10. Well, that's just 9.6. Okay, and her quiz average, that's a 92, but I have to multiply that by the weighting it gets. So multiply by 0.10, again, because quizzes were also 10%. Well, that's 9.2. And tests, where she's getting an 81% right now, weigh most of the grade. It's 80%, so I take it times 0.80. That multiplied gets me 64.8. And then when I add those all up, I end up with an 83.6. And that is actually what JC's grade is going to be. Even though it looks like she's doing amazing here, because her test average is kind of low, it's definitely dragging her down to the lower B range rather than in these A's that she had up here. By multiplying by the percent, we are allowing for that weighting to happen. Right, so that's a different type of statistic. A third way that we can display data is through a stem and leaf plot. I sometimes use a stem and leaf plot to show like test grades. Let's look at, and I'm looking at the notes packet on Peyton Manning's touchdowns through the years. And I'm going to look at this. The stem is going to be like the tens digit for me, and the leaf is going to be like the ones digit. When I look at my statistics on Peyton and his touchdowns, he's fallen anywhere from, the 20s, 30s. He had some 40s in there. So I'm going to make a stem that is going to be a 2, 3, 4. And then I draw a line to separate that. And then I'm going to go down this list, and I'm just going to start filling this in. So he got a 26, so I put a 6 here. And then he got another 26, so I put another 6. We don't put commas in there. And then I'm going to throw this in real fast. 33, 26, 27, 29, 49, 28, 31, 31, 27. And I'm just looking at that stats sheet we've got on him. And that's what his stem and leaf looks like. Now, actually, the way I do it with tests is I fill out one on paper like this, but when I write it on the board, I rearrange my numbers. When you make a stem and leaf, you want the leaves to be in increasing order. So I've got my 6, 6, 6, and the 7, but then I should have a 7, 8, 9 on the end of that. And then same thing here. I would want the 1s to come before the 3s. So I'm going to take a minute right now to fix that. Now I have it rearranged so it really goes in the correct order. The other thing you need to do on a stem and leaf is make sure that you have a key that represents what's going on. For instance, I would just make a 3 with a bar and just make something up. And then I'd say, okay, that is a 36. The reason we need to do that is because you can use a stem and leaf to maybe represent, instead of 36, maybe that represents 3.6. Or maybe a 3.6 represents 36,000 or something like that. So the key indicates that it's just 36. All right. Now we can expand on this idea of a stem and leaf and do some different things with it. One of the problems with a stem and leaf is sometimes there's not a very wide range of values. In this one I don't really. I have a lot of 20s and 30s. We might instead then split that stem and make it have 2 2s and 2 3s and 2 4s. And what that allows me to do then is I'm going to put the lower 20s on this row and the upper 20s on this row. The lower 30s, upper 30s. So this is going to be 20 through 24, 25 through 29, 30 through 34, 35 through 39, and so forth. If I do that, you can actually see this doesn't work great for Eli's data because all of his 20s were the upper 20s. And his 30s were primarily lower 30s. So he's, we learned that on the box plot. He's pretty consistent. He's always kind of in that same area. There I'd put a 37 there. And then the 49 actually has to go in the next range. So you can see that was an amazing year for him. And then you would keep your same key on that. This sometimes helps if they're less consistent, and it'll spread some of those 20s and 30s out. Didn't work so awesome for his data. This third way to look at a stem and leaf is to do it back-to-back where you can compare the two. I would do that like with 2 classes with their test scores. Rather than merging it into one stem and leaf, I do a back-to-back. Down the middle will be our stem. And looking at Eli's data and his touchdowns, we're going to have to go a little bit lower. 0, 1, 2, 3, 4. Now, on the right side, I'm going to go ahead and do Peyton over here. So we would label who's who. This is Peyton, and this is Eli. Peyton's, and I'm going to go back to the regular one, so I'm not going to split it since it didn't really help much with Peyton. And then I'm going to go to Eli and look at his touchdown. He had a year where he only had 6, didn't play this many games. All right, then he had a year of 11 touchdowns. And then here's where he kind of falls. He has a 21, 23, 24, 24, 26. I have already put these in order for us. And then a 31 year. Your stem, or I'm sorry, your key looks a little bit different. You actually have 2 of these. So you have this equals 26. But over here, when you see the 2 and the number is going to be off the back side of it, like this, that's going to be like a 23. Kind of out of room there. That's 23. You have to read it backwards. So you show on your key that you have to read those percentages backwards. Just another way to compare pieces of data. The last thing that we're going to discuss today is the normal distribution curve. This is what is sometimes commonly referred to as a bell curve. And what a bell curve does is it takes data, and it doesn't take data. Data just naturally falls into this bell curve, where there is a lot of data that falls towards the middle, and then it kind of drifts off on the upper end, and it drifts off kind of symmetrically to the lower end as well. Some things that have a normal curve might be the life of a battery, let's say. On the package, it says it's going to last, I don't know, 1,000 hours or something, 20,000 hours. I don't know what battery. Depends on your battery. But you'd put that right down there. That's going to be the mean. And then you're going to have some that last a little bit longer, but not a whole bunch. And then you're going to have some that last a little bit less than that. But typically, there's a lot that fall right in the middle. Light bulbs do the same thing. SAT scores, which we're going to look at here in a minute, tend to fall that way. Now, on something that is truly normally distributed, we have determined that there's certain percentages that will fall within, and let me go through this one more time. This right down the middle is going to be the mean. We're going to put the mean. I'm going to call that X bar. That's the mean. And then what I do is I'm going to find out what my standard deviation is. And the standard deviation basically tells you how far values tend to deviate from the mean. If you have a large standard deviation, that means your range is pretty wide. If you have a small standard deviation, then it all clusters tightly around the mean. What I'm going to do is I'm going to find the mean. I'm going to put that value right here at the middle. And then I'm going to find the standard deviation, and then I'm just going to add a standard deviation, add a standard deviation, add another standard deviation. And I'm going to subtract a standard deviation, subtract another, subtract another. And those would be the values that I put along the bottom here. When I do that, I find that 68% of the data is going to fall within one standard deviation of the mean. So 34% above, 34% below. That's 68%. Would fall within one standard deviation of the mean. Okay, and then we say 95% will fall within two standard deviations. Now, 95%, you've already used up 68%. You can do a little math and find that leaves you with 13.5% in this column, 13.5 within this column. So that's total of 95 within two standard deviations. This would all add up to 95. But specifically, these are the percents that would fall in each area. All right, that takes me to 100% of the data, or really, really close to it. It's not actually exactly 100, but really close to 100% of the data should fall within 3 standard deviations of the mean. These numbers all add up to 100. So you have this tiny little 2.5% here and 2.5% here. Let's look at an example. Let's take a look at this SAT problem. Back in 1995, they reworked the SATs and they scaled them so that the mean would be 500 and the standard deviation would be 100. Okay, and SAT scores tend to have this normal bell-shaped curve to them. Now, with that information right there, the mean and the standard deviation, I draw out my bell-shaped curve. When you make that, you put the mean line right down the middle, and then you go 1, 2, 3 standard deviations up, 3 standard deviations down. These bars need to be like equally spaced, and by the time you get to the third, you should be towards the end down there. And then I'm going to put in my mean of 500, and then I'm going to go up by 100s. So go up to 600, 700, 800. But then I'm also going to subtract standard deviations, so down 100, and down another 100, and down there. Now, with that information, and you'll have to look back at your previous graph for those percentages, unless you have them memorized, which you will need to know, by the way. What percent of the scores should fall between 400 and 600? So you're saying What percent falls within 1 standard deviation of the mean? So anything in here or in here. All you do is you add this bar to this bar, so that's 34 and 34. Then your answer to that question would be 68% of the scores should fall in that range. All right, let's try another one. What percent of the scores fall below 300? Okay, that's right here, and you're talking about anything below that. Well, all we really have is this bar that has 2.5% in it. That's what percent would fall below a 300. Let's hope that's not you. The last one, what percent of the scores fall between a 200 and a 700? Okay, so that's here and all of these. Now remember that this splits this evenly, so this is really, there's going to be 50% below it and 50% above. This right here is going to represent 50%. I don't need to add those percents up. That's 50%. And then I've got these two bars here. Wouldn't it really be easier? I mean, the only thing I'm missing is this bar. So rather than adding all that up, couldn't I just take 100% and subtract out the only thing that's not included? And that's what I would do. I would take 100% and subtract the 2.5%. So 97.5% of SAT scores should fall between a 200 and a 700. Now we're going to take a look at doing a normal distribution curve that's a little trickier, at least the numbers are a little uglier. I'm going to look at Peytons passing yards. Now, the first thing I did is I went to the chart of stats from your notes and I entered that data in list 1 and I ran that one variable statistics because a couple of things I can find in there are the mean and the standard deviation. When I did that, I got a mean of 4,100 and I'm going to round these off, just 4,182. The standard deviation is 379. With that information that I can fill in my normal distribution curve, and my mean is going to go right down the middle, 4182. And then I'm going to sit there and I'm going to add, and I just so that you know, a quick way to do that, I'm just going to do 4182, and I'm going to do plus 379, enter, and then plus 379, enter. And once I have that answer plus 379, I can just sit there and do enter, enter, enter. And you'll get all the numbers that you need. My first one, then up 1 standard deviation is 4561, and then 4940, and the very top is 5319. Then I'm going to start over and I'm going to do 4182 as my mean, and I'm going to subtract 379, press enter, and then do just minus 379, and it'll do answer, minus 379, and do that a few times so you get your numbers that you need. I'm going to have a 3803, a 3424, and 3045. Now with those values then, let's go find some percents. What percent of his seasons should his passing yardage fallen? Here are some examples. Between 3424, oh, that's this line right here, and 4182, that's this line. That just means it's these two bars. I'm just going to add those two up and say that's going to be, what, 47.5? So 47.5% of the time, he should have been hitting in that range right there, or passing in that range right there. Now that's 47.5% of his seasons. Well, how many seasons did he have there? In other words, how many pieces of data did we have? And if you recall, we ended up with, and I lost that there, I think it was 15. Yeah, there were 15 seasons there. That's something else that I should have written up here. What is in is the number of seasons that we had, and it was 15. So 47.5% of the 15 seasons. That means I'm going to type in my calculator then, 0.475 times 15. Actually, let me undo that because that looks like an X, and that's going to be kind of confusing. So I'll take this times 15. And that means, and it's 7.125. It's not going to be exact. I'm going to round it off to, or I should probably do wavy lines, approximately 7. Now what I want you to do then is I want you to go back and I want you to look at the list of all the pieces of data that we entered, all the different seasons, and I want you to count how many of them really fell between 3424 and 4182. So I'm sitting here looking at his chart, and I'm going to count how many of them fall between there. So the first one does, so that's 1, 2, 3, 4, 5, 6. I think I got 6 there that I counted up. So we said about 7, but it actually was 6. That's pretty close. All right, that's kind of the mentality that we're going with. Let's try that a few times so you understand that process. The first thing I'm going to do is ask you, but what percent should fall between a couple values? So this time I'm between 3808 or 3803 and 5319. Okay, so real quick, like that's 50% plus another 34. That's 84%. So that's what percent should. Now that's 84% of his seasons, so that's 0.84 times 15 seasons. And I get an approximation of 12.6, so I'm going to say about 13. And then I have to go to my list from my notes, and I'm going to count up how many fell between 3803 and 5319. And I have 12, I think. Now I'm trying to do this quick. If I missed one, you can tell me about it later. All right, let's try a little bit more. What percent would be less than 4182? Well, gosh, that's right down the middle. What percent is less than that? That'd be 50%. Now that's 50% of his seasons, and so he had 15 seasons, so it's 50% of 15. We don't need a calculator for that. That's about 7.5. So let's see if we look at it, how many were less than 4182? I have 7. All right, pretty good. All right, you try the last one on your own. All right, this is what you should have ended up with. Okay, now that's all I have for you. Basically, you're doing box plots, weighted average, stem and leaf, and normal distribution curves. All right, there's a homework worksheet. Hopefully you have that. Go work on that. Good luck.